Okay, so this will just be a quick video on proving this nice little neat identity. And so that just says e to the I theta minus 1 is equal to, or the magnitude of that, which is the distance of this complex number from the origin, is equal to the absolute value of 2 sine theta over 2. So if theta is positive, this is just 2 sine theta over 2, and if theta is negative, then it'll be like the absolute value of whatever that negative number is. And as a reminder, in case you haven't ever seen complex exponentials before, or you don't like them because you're a monster, e to the I theta is equal to cosine theta plus I sine theta. So that's what another way to write the complex number. So I recommend you try this and see if you can get it, and if you can get it, try getting it in another way. So the first thing you might be tempted to do is sort of just rewrite this in terms of this, and then use Pythagorean theorem with the real part and the imaginary part, and then do some algebra and get this. And I think based on that you have to do some trig identities. Or maybe you said, well, here we have some absolute values here, but we know that the right side is going to be a real number, so maybe we can square that, and then you get that magnitude of e to the I theta minus 1 squared is equal to 4 sine squared theta over 2. And so this is always going to be a positive number, and you can also pretty easily convert this into some expression of cosine. And this is also much nicer because you don't have to take the square root when you're using the Pythagorean theorem. And so maybe if you tried that, you got a slightly nicer solution. But in my opinion, the really nice solution comes from thinking about this geometrically. So what you can do is take a two-dimensional plane, which is your Cartesian, or no, your complex plane, and you take your unit circle over here, pretend that that's a circle. I am awful at drawing circles. And then your complex point e to the I theta will just lie somewhere over here. And this angle over here is theta. So now what you're looking for is, keep in mind this has radius 1, is e to the I theta minus 1, which will be somewhere over here. So this is like sort of adding up the vectors. And so in general, this is pretty close to the circle, but it won't necessarily lie on the circle. For example, you can have something that goes over here, and then something that goes out there. So what's nice is you have the length of your circle is 1, and the length of 1 is also obviously 1. And so what you have is e to the I theta minus 1, which is this length over here, is going to be the length of this third side to a isosceles triangle. So notice that 1, since it's a real number, this vector is sort of parallel to the real axis. And so what that means is you can use opposite interior angles, or whatever rule you want to call it, to say that this angle over here is also going to be equal to theta. Because these two lines are parallel, this is a transversal, and these are opposite angles. And so we can draw a picture here a bit larger, so this will be theta. This will also be theta, and this is e to the I theta, and this is the length that we're trying to figure out, which is 1 e to the I theta minus 1. And so the absolute value will just be equal to this length, but we can also just figure this out pretty easily by splitting this in triangle in half, and then this 90-degree angle. And then because it's an isosceles triangle, this angle is also split in half, so this angle is theta over 2. But then notice that you have a triangle with a hypotenuse of 1 and an angle of theta over 2. So this length is just sine theta over 2. And so what that means is that the total length is going to be equal to 2 sine theta over 2. Because this is sine theta over 2, this by similar argument, because this angle appears theta over 2, is also sine theta over 2. So put both of them together and you get 2 sine theta over 2. And so, this length represents the absolute value of e to the I theta minus 1, and you also just calculate it to be 2 sine theta over 2, and so you've proved that that is true. And you can also look at it for something down here, and this is where the absolute value comes in. This is your negative theta, and so if you consider it as theta being a positive number, then because it's below the x-axis, it's going to be a negative value. But then this angle measure over here is also theta. And so you have that this is still the sine of absolute value of theta over 2 times 2, because here again you can use the same sort of angle bisector argument, and this also works, as you can see, with obtuse angles. And so you have that this works with theta being positive or theta being negative, and this is the same thing as absolute value of 2 sine theta over 2. So you can try a couple other things from this. Maybe you can try e to the I theta plus 1, e to the I theta plus I, e to the I theta minus I, or maybe you can even look at e to the I theta plus e to the I alpha and use some other value alpha. Or maybe you can try and be creative and add up a bunch of different things and try to get an expression for that, like e to the I theta 1 plus e to the I theta 2 plus e to the I theta 3. I haven't thought about it, and maybe you can come up with the formula. But yeah, that's pretty much it for this video. Complex numbers are nice.